Hey everyone, welcome back to my YouTube channel, where we make engineering concepts clear and simple. Today, we're diving into the very foundation of engineering science, mechanics. So let's break it down. Mechanics is the science that describes and predicts the conditions of rest or motion of bodies under the influence of forces. In other words, mechanics helps us understand how objects behave when something pushes, pulls, or supports them, whether they stay still or move. Mechanics is divided into three major branches: mechanics of rigid bodies, mechanics of deformable bodies, and mechanics of fluids. Let's go through them one by one. First up, mechanics of rigid bodies. This assumes that objects do not deform when forces act on them. Why assume rigid bodies? First, to simplify complex real-world problems. Second, to focus on motion, force, and equilibrium without dealing with material deformation. And third, it's applicable in structures, machines, vehicles, and mechanical systems where deformation is negligible. Mechanics of rigid bodies is further divided into statics, the study of objects at rest, and dynamics, the study of objects in motion. Let's break down a simple but important difference in mechanics between statics and dynamics, especially when it comes to velocity and acceleration. In statics, both velocity and acceleration are zero. Why? Because the objects are at rest. They don't move at all. For example, a book resting on a table. But in dynamics, it's a different story. Objects are moving, so velocity is present. Now, what about acceleration? Well, it depends. If the object moves at a constant speed, the acceleration is zero. For example, a car moving straight at constant speed on a highway. But if the object is speeding up or slowing down, then acceleration is non-zero. Now, in real life, no material is perfectly rigid, but in many practical cases, the deformations are so small we can ignore them, unless we're studying how or when materials might break. That's where the next part comes in. When we care about how materials bend, stretch, compress, or even break under load, we look at the mechanics of deformable bodies. This includes what we often call mechanics of materials, or strength of materials, which is essential in designing safe and reliable structures. We'll explore two fundamental concepts in mechanics of deformable bodies: stress and strain. While they may seem simple at first, these ideas are the backbone of how we analyze structural elements like beams, columns, and trusses, essentially the building blocks of all engineering structures. Then we have the mechanics of fluids, which deals with both liquids and gases. It's further divided into incompressible fluids like water and compressible fluids like air or steam. We're diving into the concept of incompressible fluids, a term you'll often hear in fluid mechanics. So, what exactly does it mean? Let's break it down. An incompressible fluid is a type of fluid whose density does not change significantly even when pressure is applied. That means no matter how much you squeeze it, the fluid remains nearly the same in volume. In engineering and physics, we often assume that these fluids have constant density. This simplifies many calculations, especially when dealing with liquids like water. In terms of compressibility, incompressible fluids are considered to have very low compressibility. In simple words, they are hard to compress. This means that their volume stays almost the same, even if you apply high pressure. That's why they behave predictably in many systems. So where do we use this? Incompressible fluids are used in hydraulic systems, plumbing, and many fluid mechanics problems, especially when dealing with liquids like water and oil. Now we're diving into a key concept in fluid mechanics: compressible fluids. If you're dealing with gases, engines, or airflow, this is something you really need to understand. A compressible fluid is any fluid whose density changes significantly when pressure or temperature changes. In most cases, we're talking about gases here. Unlike incompressible fluids, we can't ignore changes in density, so when working with compressible fluids, you need to account for these variations in your calculations. These fluids have high compressibility, meaning they can be easily compressed or expanded depending on the pressure or temperature. This makes their behavior more dynamic. Volume changes dramatically under shifting conditions. Think of how air compresses inside a tire pump, or expands in a hot air balloon. Compressible fluids are critical in aerodynamics, gas pipelines, internal combustion engines, and thermodynamics. Anywhere gas flow matters, you're dealing with compressible behavior. A key subfield here is hydraulics, which specifically studies water flow and how they can be used to perform work. important in civil, mechanical, and even environmental engineering. In simpler terms, hydraulics is the study of how fluids behave when at rest or hydrostatics, and in motion or hydrodynamics. Now here's something interesting. Mechanics is a physical science because it deals with physical phenomena. But it's also deeply tied to mathematics due to its reliance on logical reasoning and equations, not just trial and error. At the same time, it's an engineering science because the goal of mechanics is to explain and predict what happens in the real world, so we can apply it in engineering problems, from bridges to engines to airplanes. So to sum it up, mechanics helps us understand how things rest, move, hold up, or even break. It's not purely theoretical, and it's not just hands-on. It's both. And that's why it's such a powerful foundation for every engineer and scientist. If you found this helpful, don't forget to like, subscribe, and hit the bell icon so you won't miss our next lesson. Got questions? Drop them in the comments. I'd love to help you out. Thanks for watching, and I'll see you in the next video. Bye.